All right, guys, what we're starting today is Chapter 1 for Algebra 2. Now, Chapter 1 is going to be a little different than the rest of the chapters because all the chapters besides Chapter 1 are going to be more central around a kind of current, a set topic, like you're used to, especially geometry, where we talk about circles or triangles. It was one concept. Chapter 1, just like Chapter 1 geometry, is going to be a little bit of everything. It's going to be a little all over the map. So I'm giving you more of that as a heads up, because once we hit Chapter 2, we're going to talk about parabolas. Chapter 3 is actually also going to be about parabolas. Because we have several chapters, and it pretty much after Chapter 1, it'll stick around a central concept. But Chapter 1 kind of goes all over the map. Now, with Chapter 1, we're going to be talking about intervals, set notation, inequalities, these here. But the first thing we need to talk about is, what is a set? A set is a collection of objects. That's all a set is a collection of objects. And the way we write a set is with braces. Braces are used to list a set's members. Sometimes we'll have to use ellipsis points. I had to look that up. But we'll see that here in a minute, because you all know what ellipsis points are. Yes. Now, our first example of a set is 1, 2, 3. So if we were going to list a set, we would use a brace, 1, 2, 3. Brace. Now, this would be considered a finite set, because there's a finite set of numbers. There's only 3 of them. 1, 2, 3. It's finite. Now, our other example is not finite. It is not, it continues on, because our positive even numbers, well, the first positive even number is 2, 4, 6, 8, dot, dot, dot. We use ellipsis points. That's technically what it's called. But dot, 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 because we need to set it. Right, because we have an infinite number of even numbers. Now, if we can't really list all of them and we use the dot, 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 we have to set a pattern for what we're talking about. So 1, 2, 3, 4, 5, or 1, 2, start again. 2, 4, 6, 8, 10, 12, going on. And then we use the dot, dot, dot to signal that it's going to continue on in that pattern infinitely. Questions about sets? Now we have types of numbers, sets of numbers. Now, in years past, I had these all on their own separate slide for each one and had them listed out. But I decided instead of wasting all that paper, I put it as one. So I'm going to be showing different slides, but for you have one there at the bottom of the first page you're going to fill in. So the most central box on the left, so the box in the most box, yep, right there, is natural numbers. And natural numbers are naturally the numbers you count on your hands and your feet. So 1, 2, 3, 4, 5. And again, unfortunately, I did not come up with that rhyme. Someone else did. But those are our natural numbers. And we do have a symbol for the natural numbers. It is an N with 2 lines. That is our symbol for natural numbers. Questions about the natural numbers? Are you ready for the next type of numbers? So the next group of numbers builds off of these here. And we have the whole numbers. And there's a whole lot of difference between the whole numbers and the natural numbers. Yeah. Well, the only real difference is it adds 0. Does anybody have a guess at what the symbol for the whole numbers is?
0 with another line.
It would, that makes sense, but it's not. That's actually called the empty set. The funny thing is, there is no symbol for it. There's no state symbol. Some will use a W with 2 lines. But for the most part, we don't talk about, or if we're talking about a set, especially sets of numbers with symbols, we don't normally use one for this here for the whole numbers. We'll just talk about it as the non-negative integers would be the whole numbers. Now, integers give us our negatives, -1, -2, going on. And our symbol for the negatives is a Z with an extra line. And part of the reason they use a Z with an extra line is because I was already taken. We haven't listed it yet, but there is already one with I. So as you notice, we're really building a number line because natural numbers gives us all of our counting numbers. Whole numbers gives us 0. Integers gives us our negatives and positives and 0. Well, what we need to add next is our fractions, our rational numbers. Our rational numbers are anything that can be written as a fraction. So 1/4, 6/5, 7/9, 9/15, 125th, 125 anything we can write as a fraction is rational. And yes, the symbol for rational numbers is Q with an extra line. And the main reason the rational numbers is Q with an extra line is because R was already taken. So any questions on these so far, these different types of numbers? Well, if we have numbers that can be written as a fraction, we also have numbers that cannot, and those are our irrational. Irrational numbers are any number that cannot be written as a fraction. So the first one, you all know, pi is an irrational number. One four. Now the next one is phi. It's going to be very, very rarely, or not at all, that you'll use phi in high school or in college. Phi. So the second one is phi, P-H-I. Yep. And the last one is E. E is used for our exponential and logarithmic functions. Exponential growth, exponential decay is where E comes into play. Now we also have other irrational numbers. Square root of 2 is irrational, non-repeating, non-terminating decimal. Any radical that does not reduce to an integer or natural number or whole number is irrational. So the 8th root of 2 is also irrational. Because we're looking for what number times itself 8 times is 2. There's not a rational number that works for that. All of those are considered irrational. So we good with all these number types so far? Now, natural numbers are whole numbers. All whole numbers are integers. All integers are rational numbers. Rational numbers are not irrational numbers, and irrational numbers are not rational. They're not together. That's why they have their own separate box. But all of these numbers are considered to be real numbers. And the real numbers have a symbol of R with 2 lines. Irrational is an I with 2 lines. I forgot to say that a minute ago. So I with 2 lines is irrational, and all of these are considered to be real numbers. And the real numbers is an R with 2 lines.
So real numbers are clearly just every number.
Yep. Except for, oh, 0 is a real number. Except for fake numbers. We call them complex numbers.
Of course they'd be complex.
Because the reason they are complex, kind of joking and not, a complex number is composed of 2 things, 1 part real and 1 part imaginary.
No, I'm not doing that.
Okay. It's an imaginary number. Yep. And we will get to those.
Seriously?
Yeah.
Of course. What is this, fairy tale class?
Now, real numbers we've had for a while, and that's why it's had the R. Now, the reason, because they actually had the concept of irrational numbers before they had negatives. And it's not that, especially Greeks, all of them didn't have the concept of negatives. They just had no reason to group them as a set of numbers. Because for the most part, especially Greeks, Mesopotamians, they didn't necessarily think of it as a negative. They just thought of it as the opposite. So -2 wasn't -2. It was the opposite of 2. It was just the opposite of it, going in the opposite direction. It's just opposite. It was what the additive inverse, which got you back to 0. So we would take 2 plus 2's opposite to get 0. So they never really considered it a group until later on. But at that point they had, because the Greeks and Mesopotamians, all during that time period, had the concept of an irrational number. That concept was there. They knew that. Yes? Mm-hmm. So, all right, let's look at this first example. The set of whole numbers less than 10. So we're at the top of the back of the first page. So the set of whole numbers less than 10. Let's write this set. So we use a brace. What's our first or smallest whole number less than 10?
1.
Almost.
0.
0.
Okay. 0.
And 1, 2, 3, 4, 5, 6, 7, 8, 9. Because we just want the numbers less than 10. For the homework, I would not have counted off. If you'd have done it, I would have marked out the 10, but I wouldn't count it off a point. Because again, for most of the homework, it's either half or whole. Because I don't like doing quarters, eighths, tenths. Now the next example we're going to do before moving on is the set of odd whole numbers less than 24. Our first odd number would be, it would be 1. Because 0 is not odd or even. So 0 is neither odd nor even, and it's not positive or negative. We'd have 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, 23. I've also done this problem for the 4th time today, so.
Good
Questions on these here? Questions on this here? Now, the next thing we're talking about is subsets. There we go. Subset is a set that is part of a larger set. A subset, for something to be considered a subset, everything in it must be contained in the other set. So,
There's an A to B. Not the whole.
So, A is a subset of B. So that symbol is subset. That is the symbol for a subset. So A is a set that is part of a larger set. Is when all, so it's a subset, is when all members of a, or set A are also members of set B. So if we look at this here, 1, 3, 15, 20 are the parts, or what we call elements of set A. Set B contains 1, 2, 11, 3, 20, 100, 15, 27. Is everything in A contained in B? Yeah. So we can say A is a subset of B, and we would write it like this here. Now, can we say that B is a subset of A? It's a larger set. There are parts of B, elements in B, that are not contained in A. Now, is A subset of A?
No.
Is A a subset of A? Guys, focus up here. Is A a subset of A? Is everything in A contained in A? So by definition, it is a subset.
But it's not a larger set.
It doesn't have to be. Subset is a set that is part of a larger set. Everything in the set has to be contained in the other.
So it doesn't necessarily have to be larger.
No, it doesn't have to be larger. It can be the same thing. Because B is also, yes, a subset of it. So any set can be a subset of itself. And there is another piece down below, but this here, you don't have to write this down. This is kind of a side note above and beyond. This here is what we call the empty set. So a circle with, or a zero with a line through it is what we call the empty set. Now the reason we have to distinguish this is because if we said 0 instead of that, the 0 is technically a number. It is an element. So the set's not empty because it has the element 0. So we have to specify this here. Now, the empty set is going to be the subset of any set. Doesn't matter what it is. Every set will have the empty set will be a subset of any and all sets. Okay? Which means that the set containing the empty set is a subset of the empty set. Because the empty set is a subset of any other set. So the set containing the empty set is a subset of the empty set.
So the subset of the subset of the subset of the empty set is a subset of the subset of the subset.
Yes. Yes, because we can just make this infinitely many subsets of the empty set, and it just goes on forever. Now, empty sets, for the most part, we don't talk about it much in Algebra 2. It shows up at higher levels, but writing subsets in set notation. So we want to write all the non-empty subsets of these two here. So if we look at the first one here, we have the set containing 4, 5. So one of the subsets for this is just the set containing 4. Yes, just the set containing 5. Or we could have the set containing 4, 5. So we're not going to talk about the empty sets because, as we just saw a minute ago, they can go, there's an infinitely many number of those, so we're going to ignore those. So for our two elements, for 4, 5, well, we have the set containing 4, the set containing 5, and the set containing 4, 5. So there are 3. How about the next one? So the set containing C, the set containing D, and the set containing CD. Now, we're not going to consider CD and DC to be two different sets. They're going to be the same. Questions on these here? We ready for the next one? So let's change it from 2 elements, 2 terms, to 3. So what's one of our subsets?
2.
Set containing 2. And then 4. And then 6. So that's all of our 1 term. We can do 2, 4, 6. So let's do 2, 4. 2, 6. 4, 6. And then lastly, 2, 4, 6. Questions on how we got these here? I do not know.
I knew I couldn't keep up from day one in freshman year, so I just gave up right now. I was like, you know what? I'll just give up the next 3 years. I'll just,
At any point, if you need me to pause,
I'll wait.
just ask.
That was until Seth told everybody to stop doing anything.
Well, how long did that work out for? Not very long. Yeah, still got the answer.
All right. Questions on C. Let's look at this last one here. E, F, G, H. Set of D. Set of F. Set of G.
I looked down.
Set of F. Set of G. Set of H. Now we can do sets of 2. So we could say E, F.
I can't write these braces.
They're not going to look like braces at all, right? Mine just look like weird squiggles.
That's what I've done. I gave up on trying to make the braces look like a brace.
They look like backwards and forwards threes.
Yeah. As long as it is clear what they should be, that's fine. So our 2's with E, so E, F, E, G, E, H. Any more with E in 2's? I think that covers them all, yes? So our next one of 2 we could say is F, F, G, F, H. So F, E, and E, F would be the same, so we don't have to relist it. And the last, there's one more set of 2. HG, or you could call it GH. So we could say HG or GH, they would be the same. Well, that covers all of our sets of 2. Sets of 3, well, we could do E, F, G. Well, and the way we do this is going to depend on how you want to keep track of it. I just keep the first 2 the same and change the last one as far as I can. So we could say E, F, H. So E, F, G, so we can change the F to G. So E, G, H.
Oh, we're still on.
There is one more set of 3.
And SH.
That's GH. There is one last one.
Oh, wait, the last one.
Oh.
1, 2, 3, 4. No. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There are 15.
What am I paying you? I wanted that food now. I have something like this.
Questions on subsets? Now, this is above and beyond. You won't see this come up anywhere else. 2 to the nth power minus 1 will give us the number of subsets, where n is the number of elements or the terms in the set. So 2 to the n minus 1 will give us that there. So our first one, we had 2 numbers in the term, so 2 to the second minus 1 is 3, because the first 2 we did had 3. The one we did after that had 4 terms. So it's not 4. That was the last one we just did. The one before that had 3, 7. The last one we did had 15. If we decided to do 10 terms because we had no time or nothing else better to do. So a 10-term set has 1,023 subsets.
I don't think this is ever been that.
I have a feeling I would lose track of terms real quick. Yeah. Intervals. This is the last thing we're going to talk about today. We will finish these notes up tomorrow. Bounded and unbounded intervals. Bounded intervals have 2 endpoints. Unbounded intervals only have 1. Yeah, so bounded intervals would be considered a line segment, and unbounded would be an array, or there are some that go infinitely in 2 directions, which we would call a line. Because this is more so geometrically, so that would just be 2 points anywhere. This is specifically on a number line. Bounded intervals. Let A and B be 2 real numbers such that A is less than B. So given 2 numbers where one is smaller than the other, we have these here. Then the endpoints, then A and B are the endpoints of 4 different bounded intervals on the real number line. So the first one we have is that A is less than or equal to X is less than or equal to B. Or in interval notation, bracket A, comma, bracket B. Now the second one is similar to the first, except they're not equal to. A is less than X is less than B. So we have parentheses A, comma, parentheses B, two parentheses, because parentheses are used when it's not equal to. Now the other two we have are very similar to each other. It's just that one endpoint is included and the other is not. A is less than or equal to X is less than B, or A is less than X is less than or equal to B. One endpoint will be included, the other will not. Questions on this here? The other type is unbounded intervals. Let A be a real number, and each interval on the real number line shown below is unbounded. So we just have one endpoint, or no endpoint possibly, and it continues on in one direction infinitely. So X is less than or equal to A, so A is our first endpoint, and it goes to infinity. Or X is greater than A. So at A, we have a parentheses instead of a bracket because A is not included. Or we say X is less than or equal to A, so we have negative infinity, comma A. And lastly, X is less than A, so negative infinity, comma A with both parentheses.
What is negative infinity?
So it's the biggest negative number we can possibly think of. Negative infinity. Incidentally enough, infinity and negative infinity are not actual numbers, they're concepts.
You just have to draw a plus like here if you want to go past that.
Yep.
Yeah, you got it, Kevin.
It's so funny, I can laugh a lot.
My brain. How do you draw this?
You turn the paper sideways and draw an 8.
Oh yeah, just turn the whole page on.
So it's been a minute since y'all have done inequalities, intervals, interval notation, because y'all did these in Algebra 1. It's just been a minute. Almost 3:30. So,
Violence is wrong, but sometimes the only way you think that,
any questions on any of this here? All right. Now, before you on anything else, I realize well, not quite. There's one more thing I wanted to talk about with subsets. This isn't anything overly important. Now, number line. Now, a number line, we can call it X. In our notation, or kind of higher level math notation, we say R1. R1 would be considered a number line. You don't have to write this down if you don't want to. Now, again, this is talking about subsets. Now, the XY coordinate plane, so the two coordinate plane are graph. Everything in the graph, well, everything on the number line is contained in the graph, yes? So we can say R1 is a subset of R2, because R2 is the two-dimensional or XY coordinate plane. Are we good with this so far? You just draw, it's really the arrow.
so smart.
Now, the xy coordinate plane is a subset of the xyz. So we can say that this is a subset of R3. So the x coordinate plane is a subset of the xy. The xy is a subset of the xyz. So R1 is a subset of R2. R2 is a subset of R3. R4, which is a subset of
R8.
5. Now R4, we could say that the fourth one is time, but really after that we have no way of actually visualizing or conceptualizing what R5 is, let alone R20 or Rn. But just we don't know what that is, because we don't know what a fifth or sixth or 20th dimension is.
So why we even like write it down in the first place?
Because conceptually we have notions of what or can be applied to it. We just don't know what it is.
What is the fourth?
Time. Some would consider time. Or space. But space would be 3. So above and beyond.
Oh, I've never had this. Never either.
Well, all right, guys. We're going to stop there for today.